I'm really a soil microbiologist from down under. Most of my time I spend just quietly underground, just doing work there. But no, very interesting things. I'm working with a little group called Healthy Soils Australia in Australia. They're groups of farmers, very, very innovative farmers, all different industries, all different regions. We've got about 1,000 farmers involved in this in Australia, but they're really leading some very, very clever solutions, both regenerating the land, but then coming into rehydrating arid landscapes, and of course, naturally, safely cooling those regions in the planet. So I wanted to sort of share all that experience, but also what's happening globally in a bigger level with you, and really come to the topic of today, new climate solutions. A bit of a pun on solutions, because we're going to be talking about hydrology and basically how 95% of the heat dynamics of the blue planet is governed, in a sense, by water. And in a sense, it's a process and a whole influence that we've, in a sense, ignored in the last 60 years with this climate debate, because we were so focused on the CO2 rise and the symptoms of that, and of course, what do we do to address the CO2? And in a sense, water is just the key process that naturally drives the hydrology, drives the heat dynamics of this planet. And really the question is, can we actually look at those processes and see if they are part of the solution? But, okay, no, please come around. No, no, okay, because no problems, interruption. And it all comes back to the thing that Dee sort of talked about, because at the end of the day, it's where do we humans have agency? What is it that we can do? Because where are the practical points of influence? And of course, that is that simple word that she said, the sponge. How do we regenerate the Earth's soil carbon sponge? So in terms of take-home messages, it is that sponge, it is the regeneration of the sponge, which is our key tool, our key point of agency, but also it enables a whole regeneration of biosystems, gives us the water, the food, the biosystems, the social stability we're going to fundamentally depend on in the next 10 years and beyond, but also allows us to naturally and safely cool regions in this planet. And so in essence, that's the new climate solutions we want to talk about. But let's get into some of the details of that. Basically, we've all known for the last 60 years, and we've all seen, actually I'll do in the middle here, we've all seen the curve that Charles Keeling sort of set up in 1958, or from 1958. Okay, that's CO2, this is time, and basically CO2 goes up. It's 406 parts per million. It started at 280. Okay, and what Charles Keeling showed wasn't just that CO2 was going up, but that it was going up in a quite clear pattern where every winter we were emitting carbon, and every summer, spring, of course, we were drawing down carbon from the air back into biosystems. And so we had this constant springtime, summertime drawdown, and then winter emission. And the point was that we had a deficit of some 10 billion tons of carbon per annum every year. And basically, it's that deficit, that accumulated deficit, that was causing the CO2 rise. And of course, for the last 60 years, that's been our whole focus in our climate, global warming discussion. Clearly, we have CO2 rising. No question whatsoever, CO2 is a greenhouse gas. We know it does about 4% of the heat dynamics of this blue planet. It's a major or partial contributor to the natural greenhouse effect, and certainly by increasing it, we are accelerating that greenhouse effect. We know that effect is serious because if we draw the Earth, we know that we have incident solar radiation, that's sunlight coming into the Earth all the time, and on average at the top of the troposphere, 240 watts per square metre. Constant heat energy coming into the top of the troposphere. And basically, to keep a stable climate, it's just simple physics and simple climatology that we need 342 watts going back out. Obviously, otherwise the climate heats. But it's not, because now, because we've increased the greenhouse effect, the retention of heat by this planet, we only have 339 watts per square metre going out. So there's about 3 watts per square metre which is being retained by the Earth because of this enhanced abnormal greenhouse effect. So it's a 3 watts per square metre warming, which is really what the global warming is about. And it's significant because obviously it's changing the climate, but we can see that is less than 1% of this incident solar radiation. And it's important to understand that context because, hey, 1%, we may be able to do something about it. But of course, here we're talking about heat dynamics, but we've got to now translate, hang on, here's the CO2 increase and how do they relate and what other factors may be involved. And of course, we're raising that proposition. The water, what role does water play in this? But we'll come to that as we go through in a bit more detail. Okay, no problems. So we've already set the scene, you see, because we've sort of said we've got 10 billion tonnes of carbon every year that's adding to the atmosphere. And so in 1978, your president, Jimmy Carter, basically sort of said, look, I'm getting this warning from scientists legitimately, and basically he issued a reference to the Scripps Oceanographic Institute in San Diego and Los Alamos to say, look, do the analysis and tell me what is the consequence of this greenhouse warming, what are the risks to America, what are the impacts to America and globally, and really give me a reference, give me the grounding, where do we have to be and what do we have to do. So that was Jimmy Carter in 1978, right? 40 years ago. And of course these institutes, they diligently did that work, but they defined the thing very much on the basis of this CO2 effect. You know, they sort of said, okay, we've got this symptom, we've got this CO2 increase. Obviously it's abnormal. And so how do we look at the greenhouse effect of that CO2 rise? They were well aware, and climatology 101 right from the 40s, 50s, you know, was fairly cognizant, 95% of the heat dynamics of the blue planet is driven by water. But they basically excluded water from their analysis for 2 reasons. The first thing is because water is so dominant, they assumed that, look, we humans could not possibly have influenced that aspect of the world's heat dynamics to have had this effect. And secondly, because water, again, is so extremely variable in time and space, location and seasons, it's impossible to model mathematically in the reference that the president had given them. You know, can you mathematically model and define scenarios and consequences, what will happen? The point is that they basically focused on that CO2 component of the greenhouse effect, assuming that that was the key problem and that's what we were having to address. Because of this analysis, though, really for the last 40 years, the world has been really focused in that linear concept of the CO2 greenhouse effect and what's its consequences in global warming. Shortly after, in 1988, the UNFCCC, the United Nations Framework Convention on Climate Change, basically was formed and took on a global reference to say, look, we must prevent dangerous climate change happening, and all nations in words committed themselves to it. And out of that they formed the IPCC, the Intergovernmental Panel on Climate Change, and for the last 40 years those scientists working in the IPCC have been basically, again, doing this sort of analysis, looking what are the consequences, the impacts, the scenarios from this rising CO2 increase. but very much focused on the CO2, leaving aside a lot of the hydrological and other factors. Again, too complex and too difficult to model. Okay, so we, for the last 40 years, have looked at this problem from very much that CO2 angle. And so when we're talking about new solutions in climate, we're really sort of saying, okay, can we step outside with the elephants and start asking questions from the other perspective? Because 10 years ago, or actually no, 2005, so that's now 13 years ago, Joachim Schellenhuber and a whole group meeting at the Hadley Centre really did a new analysis and said, look, it's not just the CO2 rise that's a problem, it's actually the dangerous extremes in climate that are already accelerating and happening well in advance of the 2,100 scenarios that this IPCC analysis had sort of given warnings about. And these extremes were actually already impacting seriously on populations, food productions. And they're quite severe. I mean, and we've talked about them, the hurricanes, the increased storms, whether it's Irene, Sandy, what have you, the flooding and the damage, as Didi has sort of shown all over the world from that, but also the droughts that are as a consequence of that, the aridification, the systemic aridifications of large regions, the increased wildfires, and of course things like sea level rise. And the point about all of those factors, all of those impacts, they are all hydrological. They're all driven by actually water, either the excess or the absence of it, triggering things like fires, droughts. And so the analysis was very clear. These extremes, these positive feedback, dangerous feedback loops were already accelerating. And particularly in countries like Australia, and in fact all Mediterraneans like California, the Middle East, the Mediterranean, South Africa, we've had a process. If we think again, there's the Earth, there's the equator, you've got the heating, and we've got these Hadley cells, which causes air to rise from the tropical heating zones. And of course, it rises up and descends as dry, hot air. And because of the heating of the planet, this has expanded both northward and southward by some 300 kilometers. Okay, so the intensifying heating from this whole greenhouse effect, from this 3 waters already causing that. And of course, this extra heating has forced the cool, moist feral cells, it has forced these cool, moist seral cells, which really drove the rainfall in Mediterranean climates, the reliable winter rainfall, has forced that further towards the poles in both cases. And as a consequence, from 1975 already, the southwest of Western Australia was already aridifying, and a 20% decrease in rainfall, a 30 to 40% decrease in stream flow, soil recharge. Because again, it was rainfall, but also evaporation factors. So we were aridifying, and the same thing applied here in California. I don't win a prize for drawing the country, but basically the whole southwest of the US, again, under that aridification. Same thing is the Middle East. Okay, Spain, right across to Syria, basically has been aridifying. And of course, we're already seeing the consequences of it. For the last 15 years, we've had farmers who've been farming the Fertile Crescent in Syria, for example, for the last 10,000 years, abandoning their farms, moving into Damascus, Aleppo, because their soils, hydrology, everything has collapsed, can't grow food anymore, moving into these urban concentrations, and of course, we know as a consequence we end up with social collapse, social crisis. So this systemic aridification, just one of those fundamental consequences of these climate changes that are already occurring. So the whole point, that was 2005, dangerous climate change. Okay, dangerous climate, actually not just change, basically extremes, right? And it's these extremes that become then the really dangerous consequences. And in a sense, that's the world we're now facing, intensifying dangerous climate extremes, and the issue, what can we do about it? Now finally in 2015, after lots of political work and false starts with Kyoto and what have you, the IPCC, Christina Figueres in Paris, was able to pull down a general agreement to say, look, let us all agree to try to achieve zero net carbon emissions. Zero net carbon emissions. So in the Keeling curve, they're saying, okay, can we actually try to get back to neutrality where our emissions and our drawdown of carbon, in a sense, offset each other, and we end up with a near zero net. And that's very laudable, and of course to do that, there's been a big agreement, a move. How do we increase the drawdown of carbon back into the by the biosystem, back into soils, and carbon sinks? And of course, yes, we have to do that. Of course, we have to continue to try to reduce, I'm drawing the arrows the other way, we're trying to reduce the amount of emissions, and definitely that has to continue. Nobody is for a minute suggesting we don't have to reduce our emissions. But the power is, can we actually accelerate that drawdown of carbon back into the biosystems? Every year, some 120 billion tons of carbon is drawn down by green plants back into the biosystem. But it's not good enough, because every year 130 billion tons of carbon is actually emitted, which is where we get this 10 billion tons of carbon deficit. But we can increase this, because at the moment the residual biosystem that we have, the land surface still covered by green photosynthetic vegetation, is perhaps half of what it was 8,000, 10,000 years ago. Okay, again, there's all the data, the numbers, we can go through them, but basically UNEP very clearly defined, yes, we have done so much degradation of forest, of grasslands, we've created 5 billion hectares of man-made desert and wasteland over that 8,000 years. And the issue is, can we increase the drawdown of carbon by regenerating that biosystem? And so what we're talking about is, yes, how do we do that? How do we enhance that? There's a bigger problem, however, because while this might be able to sort of slow down the emissions of CO2 and flatline them, well, we're up here now, of course, it won't bring that CO2 down. To bring the CO2 back down, we not just have to do 10 billion tons to offset our current net emissions, we might have to do another 10 billion tons per annum to actually draw back heritage legacy emissions that we've basically emitted previously. So the target might even be bigger. It might be 20 billion tons of carbon per annum. And the good news is, yes, we can do that. We can do that through land regeneration by extending the area, the productivity, but particularly the longevity of green growth. Okay? But none of this is possible, and this is a key point, none of this is possible unless these biosystems have water. Okay? Because for these biosystems to fix carbon, to draw down carbon, they need water. And that water can only come from the soils. So the whole take-home message from can we draw down, can we try to balance this, is we must regenerate the Earth's soil carbon sponge, because only that water can enable this drawdown to operate. Okay, so that's really important. That sponge is fundamental to that whole photosynthetic potential being realized. But we have another problem, okay? This is another problem, because even if we are able to draw down 20 billion tons of carbon, And we can. You know, innovative land regeneration can do that. We're going to Sweden to a conference, negative net emissions, and yep, here's the evidence, 20 billion tonnes. Jim was talking about that as well. Yes, we've tested it from all angles. Yes, we can do that. But even that's not good enough. Because even if we draw down 20 billion tonnes, even we draw down 50 billion tonnes, the oceans contain 30,000 billion tonnes of carbon. And as we draw down more carbon from the air, the oceans say, thank you, can I re-equilibrate some of the carbon that we've been absorbing from all your emissions over the last 8,000 years back into the air, because it's a buffered equilibrium system. And so it may take 100 years, 1,000 years for drawing down carbon before the CO2 content gets anywhere back to pre-industrial human intervention. Schellenhuber has told us dangerous climate extremes are already happening. We're already seeing those: flooding, droughts, aridification. California is on the cusp of collapse. That's why we went there. No more snowpack. No more groundwater. No more coastal ranges rehydrating landscapes through fog and mist. Wildfires in winter. The Napa Valley burnt in winter. Winter was when these Mediterranean areas should be getting their moist, cool air. Fires were unheard of in Mediterranean areas in winter. Okay, the Napa Valley burnt last winter. So the point is, we're getting these climate extremes, and we haven't got 100 years, we haven't got 1,000 years, we've got perhaps 10 years unless we balance the system. So this comes to the second key point we want to talk about. It's not just regenerating the Earth's soil carbon sponge, but how do we naturally, safely cool regions and the planet? And again, very audacious. Nobody's actually talked about it. Well, some people have, clouds and what have you. But the point is, how do we bring that back into the debate, not just as a debate, but as a practical grassroots reality? How do we practically cool, safely cool regions and the planet? So that's exactly the challenge we've given ourselves. Okay, so this has really been to set the context of what we're about. You know, how do we actually regenerate the Earth's soil carbon sponge? And of course, how do we naturally cool the planet? We've always said why we have to do it, and I suppose the next question is, well, if this is why we have to do it, let's get busy and ask what is it we have to do and how do we do it? Logical, right? So what is it that we have to do? And of course, the easiest place and the only place we can go to say, well, look, what did nature do? You know, how did nature create this biosystem? How did nature create the Earth's hydrology? How did nature create the Earth's natural cooling? Okay, because it was 342 watts in, 342 watts out, stable, right? Stable for hundreds of millions of years. Hey, how did she do it? Okay, and to do that, we just go back into nature and look at all the evidence, very clear. And we go back to 420 million years ago when I was a bit younger. I'm getting old. And basically 420 million years ago, we had oceans, we had rock. Dry, arid, hard rock. No life on land. There was complex multicellular life in the ocean after the Cambrian explosion, but that life depended on nutrients leaching from the rock into the oceans. That was a limiting factor on ocean life. And life's pretty competitive and pretty aggressive, and so straight away life sort of said, hey, if I can get onto that rock to solubilize nutrients, I've got a competitive advantage. And it did just that. And so it grew tubes of cytoplasm basically onto the rock with enzymes to solubilize essential nutrients. And of course, these are our fungi. So fungi grew from the estuarine edges onto the rock to solubilize nutrients to drive life processes further. But fungi are just like us. They're heterotrophs, actually biochemical. There's nothing closer to us as animals as these fungi. Okay, and they're just like us, they can't fix their own sugars. They can't make their own energy. Only plants and algae can do that, and some bacteria. But basically, they needed to form a relationship, a symbiosis, with something that could give them sugars. And of course, in the ocean, there were plenty of blue-green algae. So these fungi and these algae got together, made a deal, and basically said, look, let's form a lichen. And we see those lichens all over this planet still, dissolving rocks, dissolving our buildings, our concrete, our wood, our cars, you name it. Lichens are eating it up, biodegrading it, having lunch. Okay, and those lichens, in growing and moving on, leave behind organic detritus, the cell walls of those fungal, algal, lichen cells, organic detritus. And that organic detritus can hold water. It creates sort of a mixture of mineral particles, organic material, can hold extra water. And that enabled very rapidly, plant life to evolve from lichens to mosses to ferns to cycads to gymnosperms to angiosperms, and about 50 million years ago, grasses. Parallel with that plant evolution, of course, we had the herbivores, the insects, and everything that was feeding on those biosystems. Very rapidly, that process of pedogenesis, of soil formation, because soil is simply a mixture of mineral particles and organic detritus, enabled life to extend right across the 13 billion hectares of ice-free land on this planet. Okay, so within 100 million years, we had a planet which was the Carboniferous Permian, just lush, deep forests, deep organic soils, teeming with life. In fact, so teeming with life that the drawdown of carbon got down to carbon levels in the atmosphere of 100 parts per million. When life had started on land, it had been 7,000, 8,000 parts per million, and had drawn all that carbon into those forests. And of course, that's where we get all our coal, fossil fuels from that Permian Carboniferous fixation of carbon through these plant materials. Okay, so what we had 420 million years ago, but we're going to have that same story now every day. And again, think of it, this is exactly what happened on your Great Plains after the last glaciation. So this is it. So basically, if you just have hard rock or solid rock or compacted soil, or, stardust. I mean, 4.6 billion years, it had a supernova, created stardust, created the planet of these rocks. And these rocks are made of nutrients, whether it's phosphorus, calcium, zinc, magnesium. There's mineral particles amongst all of that. So basically, that was, in a sense, what the Earth, what the rock was like 420 million years ago. You put a drop of water on that, and as Didi has showed us with a flower, it just runs off, right? No effect. And what life did, just as Didi showed us with the bread and the sponge and the whole pedogenesis process, life basically, these lichens grew on this rock, solubilized them, and what they did is they created exactly the same mineral process. How many we got? 1, 2, 3, 4, 5, 6, 7, right, 7. We don't want to lose any particles, or we can actually draw, some of them are broken up to little clay micelles, right? No problems. Okay, so basically what life has done is basically solubilized these, broken these up, and left organic detritus between those particles. And this detritus, just for figuratively, think of it as little carbon bed springs, right? Okay, and you straight away you get the kids out and they want to bounce on it, right? Sponge. And in a sense, that then goes from a rock, which has a bulk density of 2.6 to 3.5 grams per cc. That's the weight per unit volume, to a healthy soil, which has a bulk density of about 1.2 grams per cc. So straight away you can see that healthy soil is made up 66% by nothing. Air. Voids of, just air, nothing. I mean, air is something, of course, so I should be precise. But the point is, it is made up of voids. And that's as simple as that. You see, nature has simply taken sunlight, CO2, water, created carbon, through these plant processes, microbial processes, just added those to this matrix, this mineral matrix, and has created a healthy soil, which is just made of mineral particles and these bed springs, or these carbon detritus. But what's powerful about a healthy soil, and really comes to the guts of our whole sponge discussion, now we have 66% of the volume which is available for infiltrating and retaining water, just as Dee Dee showed us in her bread example, right? Now this soil can infiltrate water, retain water, and sustain living plant growth for far, far longer, the longevity of plant growth. Because of these voids and because of the surfaces they've created, this healthy soil can vastly increase the availability of nutrients. Here we had essential nutrients for plant growth, but they were all locked up, unavailable, inaccessible. Now we have the phosphorus, the calcium, the zinc, in a sense all exposed for microbial activity. So the bioproductivity of that soil increases exponentially simply by creating these surface exposures, just by having the voids, by having nothing. Because we've got nothing in this soil, voids, the rootability of this soil vastly increases. So roots can grow and proliferate and penetrate. Instead of 6 inches, they can go down to 6 feet, 20 feet. So the volume of soil resource that is now available for plant growth and the drawdown of carbon that we talked about earlier is, again, exponentially increased. So the whole bioproductivity of these healthy soils, the resilience of those soils, the capacity to infiltrate, to buffer, to extend life, vastly increases. In a sense, this is what nature did to create the biosystem, to create the hydrology. And again, in a very simple form, that's all we have to do. All we have to do is just do what nature did. We use plants, we use microorganisms. Okay, so here we have our plant, we've got sun, CO2 and water, we've got photosynthesis, and we're putting stable soil carbon into the soil because the fungi and the organisms that convert the sugars from photosynthesis into stable soil carbon, which is just this organic detritus or bed springs. And that's exactly what nature did. She just took sunshine, CO2, water, through plants, made sugars, made stable soil carbon. Okay, so that's what nature did. That's how we created the biosystem. That's how we created the world's hydrology, the Earth's hydrology. And of course, that's how the Earth ran 95% of its heat dynamics and its natural hydrological cooling. And so for us, it's again very, very simple. If we've got to draw down 20 billion tons of carbon, if we've got to rebuild this sponge, it's easy. We say, hey, let's just copy nature. Simple. Okay, so how do we copy nature? We've got the model there. So we sort of go back to the textbook, go back to primary school, and it's all as simple as A, B, C. And again, here we go. Here's our plant, because we know it's all about plant growth. And it's all about ABC. Like it's that simple. All we have to do is what nature did. It's all about ABC. A is about agriculture, both in terms of field cultivation, but also now urban agriculture. We'll come back to that later because it's really powerful. It's a really important, empowering breakout that we want to talk about. And agriculture is, again, where we've been dominant because we live above the ground and we're all about maximizing yield, weight, okay, because that's what we are, alpha males, maximizing weight, yield. And we're still in that game, right? So A is okay. But what we don't recognize, because we live above the ground, we only see things above the ground, but we're only seeing 30% of the biomass which is in the tops of the plants. What we tend to not see is the 30% plus that is in the root systems. If you go to your bluegrass prairies, you've got root shoot ratios of 5 to 1, so already 80% of the biomass is down under, not up here, for a very good reason. But the point is we just see things above the ground and we sort of miss some of these very important things. We also miss, there's 60% there, there's up to 40%, 30 to 40% of the nutrients that are actually exudated out from the roots as sugars and amino acids and various sort of sugar substances, and these are critical for feeding this microbial ecology that drives the formation of the healthy soils. So these support a vast population of the fungi, the bacteria, the protozoas, the nematodes, the actinomycetes, the collembola, the earthworms, that whole life in the soil. There's 10 times the weight of living animals in a healthy soils down under than there is animals or humans grazing above it. And all of those organisms are driving the solubilization, fixation, access, uptake, cycling of nutrients, constantly just driving the energetics and nutrient availability and productivity of those systems. So 10 times the biomass. These fungal hyphae, 25,000 kilometers of fungal hyphae per cubic meter of healthy soils. Twice the diameter of the earth per cubic meter. We count them, but not with a ruler. But the point is a massive proliferation of fungal hyphae growing all through these healthy soil systems, again, solubilizing nutrients from surfaces, fixing nutrients, accessing, taking up, cycling nutrients. So massive activity and diversity in the life of our soils. And so as Didi mentioned, yes, you can put a spade in the soil. They'll eat the spade before you hurt them. But the point is that that soil is a living organism. It's a living microbiome. And really it's managing and enhancing that microbiome, as we'll show in a second, is critically important. Okay, so agriculture is important, but we've got to look at these other parts. We tend to forget them. But also it's not important, or what's not important is how much yield we've got. What is the weight of yield we produce above ground? That's fair enough. But what is really important, what happens to every gram of carbon that was being fixed by photosynthesis? Okay? Not how much we produce, but what happens to it. And there's only two things that can happen to that carbon. And only two things that have happened to that carbon for the last 420 million years. Two things. It can either burn or oxidize. Of course, back to CO2, can't it? Or alternatively, it can turn into stable soil carbon. Okay, and here we are. We're back to this situation. It can either oxidize off or turn into bed springs. Pretty simple. Okay, and so our whole future management of biosystems is all about BC ratios. How much do we let burn and how much do we let get fixed into our stable soil carbon? We just talked a second ago about the tall blue stem prairie grasses, root shoot ratios of 5 to 1. Yeah, they're putting 80% of the carbon they fix into the soil, building healthy carbon, building sponges, building bed springs. And you go back to this story with the bluegrass. Okay, if you were on the Great Plains 9,000 years ago, you would have had glacial outwash till. Clays, rocks, gravels, swamps, but just mineral wasteland. And in the space of that 9,000 years, it's this process, these tall bluegrass, prairie grasses, pumping carbon into bed springs that has created some of the world's most productive soils, 10 meters of beautiful prairie soils, 8% carbon content, able to retain, infiltrate rain, retain that rain, extend longevity of growth, green growth, maintain massive populations of herbivores, resilient, productive biosystems, until we came along. But that's another story. Okay, so the capacity of these systems to grow, this capacity to grow healthy soils and fix carbon is prodigious. But then we come along. And what we come along is, we come along both trying to grow things better, but in trying to grow things better, and I don't want to be rude, we sort of have this moron agriculture, M-O-R-E-O-N, right? Moron agricultural strategy. Okay, and we add more, we can clear, okay, let's go through it. We can clear, we can burn, we can cultivate, we can over-fertilize, we can irrigate, we can fallow, and perhaps worst of all, we can add biocides.
I'm going to translate a couple terms there. Cultivate is tillage or rototilling, that kind of thing, and fallow means to leave the land bare, not grow anything. So
Okay.
bare fallow. Yeah.
Right, but they all do the same thing. They all oxidize carbon from the soils back into the air. Okay, all of these processes in excess, I mean, let's not be pure about it, but in excess, all of them are driving carbon, burning off bed springs, putting it back into CO2, collapsing soils back to compacted, impervious rock, flour, lower productivities. So the tragedy is, in a sense, what we've been doing in our agriculture is we've invested now 40% plus of the net value of our agricultural production into these inputs that are actually driving this CO2. And of course, a lot of the CO2 comes from our fossil fuel use, but for the last 6,000 years, well before we were using fossil fuels in any quantity, we've been oxidizing carbon from the landscape. Okay, we used to have 8 billion hectares of primary forest on this planet. We've cleared 6.3 billion hectares. We've cleared 6.3 billion hectares, and basically some of it's regenerated, as in the US, in the North New England areas, in your northeast, but we've now got 3.5. So we've gone from 8, cleared minus 6.3, and we've basically regenerated, so now we have 3.5 billion hectares of forest on this planet. We burn every year, Jim was into this debate, we burn every year 350 million hectares of forest. 10% of that residual we burn every year. Every year we burn some 2 billion hectares of grassland, crop stubbles, and rangelands, all driving CO2. As Dee Dee said, we cultivate the land. When we cultivate the land, we expose it to ultraviolet radiation that kills the microorganisms, and of course it oxidizes carbon. We add excessive fertilizer. Every gram of excess nitrate, for example, we add to the soil, as in a compost process, oxidizes 30 grams of carbon. That's just the biological composting reactions. Okay, we irrigate, and basically, again, we're just accelerating, or we're restricting the fungal growth, we're sort of stopping, different organisms growing, restricting the bioproductivity. We fallow, obviously that's just starvation, concentration camp starvation. If the fungi haven't got exudates, they can't grow, and everything just slows down and dies, or just sits in a resting dormant stage until plants come back again. And of course, if we add biocides, it's just killing all these things outright. Okay, so we've done an enormous lot of damage. Conversely, in a sense, this is what regenerative agriculture is all about. We can focus on C, and the question is how much of these roots and these root exudates can we turn into humates? That's humus, you know, all the different fulvic and humic acids. So this whole category of humus, effectively the composting type process. So how do we maximize that? And the other important thing is these mycorrhizal fungi, these fungal networks, a 25,000 kilometers of fungal network. They're all made out of chitin. It's a glucosamine. When the fungus moves on, it leaves behind the cell wall. That chitin cell wall turns into compound glomalin. Yay! And glomalin and humates then form the glue that aggregates soil and actually creates bed springs, right? To bring it back to bed springs. This is then the stable soil carbon, but even the litter up here, or even the stubble or the litter, right? The plant material that we haven't harvested as grain, nature involves these other very, very clever things. They're called mobile biodigesters because they're trying to, just what you're saying, they're trying to get this stubble, this plant material back into the soil, and they develop these mobile biodigesters, and they were big bags, they call them rumens, full of bacteria. Okay, but these things had to move around, so they didn't have wheels, forgot about wheels, they put legs on these things, and they've got a business end with ears and eyes and a mouth, and they've got a business end out here which is putting biofertilizer down and stable soil carbon, and these things actually produce protein. Okay, so nature basically evolved these mobile biodigesters deliberately to do what you just said, to turn optimum bacteria conditions, to turn these cardboard litters, because if we didn't do that, all this litter goes up as fire. Okay, so we've got this beautiful thing. Do we either biodigest or do we burn? And if we burn, we go back to deserts. We go back to hard rock desert.
And that's what we're seeing in California, is that they've gotten rid of their mobile biodigesters, and there's all this fire kindling building up on the landscape.
Yeah, so if you don't eat it, it's going to burn. And the first lesson of ecology, if you can't beat it, you eat it. That was Odom. Come on, you read the book, you know. Yeah, go for it.
And the hooves break up the surface soil.
Absolutely. And so there's a lot more ecological advantages because these herbivores, they're moving around, they're breaking up surface soil, they're spreading seed, they're spreading biofertilizer. So the wise integration of herbivores, particularly in grasslands, critically important. Grasslands evolved 50 million years ago, and they exist only in a symbiotic association with the herbivores. If not, those grasslands will burn and that whole biosystem crashes back to desert. Okay, so really it's a absolutely knife-edge, ecological balance, grazing ecology. And of course, we manage this. So the important thing is we manage all these things, and we can manage B and C beautifully through just smart, ecological, regenerative agricultural practices, which is, of course, what Adam and Paula and Dee and, you know, all the practitioners about regionally, locally, saying how do we make this thing sing and dance for us? How do we make C dominate?
And where does methane production by the ruminants fit into this?
Right. Okay. Good. Let's look at methane. Yeah, it's good. No, methane, because, I mean, no, these are very, very important questions. You, me, anyone with a gut produces methane, right? Because we've all got anaerobic bacteria. So these things produce anaerobic bacteria, no question. And of course, under anaerobic bacteria, we produce methane. But also, because these herbivores create green grass, because, as I just said, they are the critical things to keep that ecological health of those grasslands and stop them from burning, that green grass, and we'll come back to more of this later, but it's really clever, nature's clever, it produces, of course, transpiration. It produces, of course, water vapor, right? Water vapor. And when sunlight hits water vapor, it photooxidizes and produces hydroxyl ions and hydrogen ions that form bicarbonate ions, right? So you've got sunlight on water vapor photooxidizing the water vapor molecule into hydroxyl ions and bicarbonate ions. And basically these hydroxyl ions are, as you know, free radicals, enormously aggressively oxidative, and they will basically turn that methane rapidly into CO2 and water. Okay? So we've got this process. Now a healthy green pasture will produce about 100 times the hydroxyl radical photooxidation than the herbivores grazing it have the potential to produce. 100 times. There's also methanotrophs in the soil, but hey, that's just the icing on the cake, right? But the real guts is this hydroxyl thing. Now, methane has been 700 parts per billion through the last couple of 10 million years plus in the atmosphere. We've had massively increased and higher numbers of herbivores on this planet. You know, if you look at the buffalo, if you look at the wildebeest, if you look at the springboks, you know, all these natural grazing things, far, far higher things. And so basically, we've had far higher methane production previously, but methane levels in the atmosphere have stayed constant at 700 parts per billion, thereabouts. Recently, they went up to 1,700 parts per billion, and of course that was due to Russian oil gas fields after Yeltsin and the USSR breakdown, not having any maintenance for 10 years, and the fugitive emissions were prolific. They've now gone up to 23, and it varies from place to place. And again, some nations have been fracking. And of course in fracking, we don't know which, but apparently there have been, some nations have been fracking, and again the fugitive methane emissions from that fracking are prodigious. But there's a patsy in this game. They're called cows. Okay? And so really it's a really neat thing, because cows can take the blame. Hey, these cows produce methane. We just look at, yes, a cow does produce methane. We, you, me produce methane. But cows are the patsies. They can be vilified, right? Because they produce methane. But the point is, these cows are actually maintaining these healthy green pastures, maintaining that photooxidation potential, particularly at high latitudes. And the real issue of methane, and it's not in the literature, but it's really the real issue about methane is our methane hydrates that are sitting in high latitude, sedimentary, ocean sediments on continental shelves. They're bubbling up. The Russian Arctic is now like lemonade with methane coming up.
Tundra.
And the tundra is releasing methane. And the only thing, and methane previously to our knowledge has caused mass extinctions. You know, bigger methane burp is one of the most dangerous things we face in this extreme climate over there. And the only thing that's going to save humanity or much of life on Earth from a methane burp is cows. Because if those cows are there, or the caribou or whatever, producing enough sustainable green pastures to produce enough photooxidation, enough methane, enough hydroxyl radicals, yeah, we've got that balance. We've got 100 times the hydroxyl from green pastures compared to the methane from the cows. So what we've been talking about, in a sense, this whole different picture of what's the new climate solutions, how do we step outside of the tunnel, the black hole we've created for ourselves on the CO2, and sort of open new windows and open new opportunities laterally by embracing this hydrological dimension. But the key point is, we've gone through why, we've gone through what, we've gone through how, the ABC, and it's all about rebuilding the Earth's soil carbon sponge. See, we didn't go through all that, did we? Can I just backtrack a little bit? Because I just wanted to make a point. See, we got sidetracked. I've got ABC here. So we say, look, the whole critical thing is the balance between B and C. But of course, we've left a field here vacant. And in nature, there's never a vacuum, there's never a vacant thing. So we've got to have another thing, D, which are the dividends. And this is very important because this is really the guts of agriculture and where we're going. If we put carbon into the soil in C, for every gram of carbon that we put into that soil, as we've seen here already, for every gram of carbon, we can hold 8 grams of extra water. Okay, and you can see that from the sponge, the bed springs, you know, the voids. Hey, we can massively increase the water retention, infiltration, and then longevity of green growth. And that's the important thing to understand. You know, like all of our Green Revolution stuff where I started research, I didn't tell you what I've been doing, but when I started as a researcher, was all about how do we increase the yield of plants, Green Revolution, right? And we do genetics and fertilizer, and if we can get a 30% yield response, we get a new white lab coat, a clipboard, and line up for a Nobel Prize, right? It's big stuff. But basically, at best, we can do 30%, 40%. But if we increase the longevity of green growth, you know, there's a rain, we've got a sponge, instead of the soil drying and we've got 10 days worth of growth, we've got 100 days of growth now because of the sponge. We've increased the longevity of green growth 1,000%. Just through building the sponge. So the multiplier effect of longevity of green growth and extending drawdown, extending productivity, extending resilience is powerful. So 1 gram of carbon, 1 gram of carbon, 8 grams of water. Every gram of carbon we put in the soil massively increases the biofertility of that soil, as we've explained, as the nutrients become available. 80% of the fertility of soils isn't about how many nutrients in that soil in total, you know, how many nutrients in total. It's about the availability of those nutrients. It's about the microbial solubilization, fixing, access, uptake, cycling of those nutrients. So the whole business about fertility is about the microbial ecology of the soils, not the content or how many morons we put on. Well, yeah, but no, we're not going to answer that because it's, yeah, it's all part of the game. Okay, the other thing, every gram of carbon we put into the soil, as we've said here, massively increases the rootability, the volume of soil we've got access to. Powerful exponential increases. And the same goes with then the microbial activities, disease resistance, resilience, productivity. The point we're making with D is simply by increasing bed springs, we can drive productivities, as nature has, massively. You know, we've got rainforests on sand dunes in Queensland where I was working when I was working in CSIRO. The world's most bioproductive terrestrial ecosystem, effectively on crushed glass with next to no nutrients in it, but every molecule is moving 1,000 times faster and therefore giving that productivity because of this microbial activity, right? The point being though that, see, this is in a sense how nature drives productivity. You know, not by Mack trucks putting fertilizers on, not by inventing biocides and all that sort of, not by cultivating, simply by increasing soil carbon. More powerfully, because of these dividends, because of those dividends, we negate the need for all this moron stuff significantly. Okay? Because why do we need it when we got carbon bed springs? And so our innovative farmers are doing 100% of the yield, but they're getting 300% of the quality, the nutritional integrity in their food grains. They're doing it with less than 20% of the inputs, less than 10% of the risk, 300% the reliability, and 500% the natural capital, asset, land, soil regeneration value. You see, these are dividends. Okay, so the whole basis of regenerative farming, the whole revolution in agriculture, taking agriculture from the 19th into the 21st century, is all about rebuilding healthy soils, rebuilding that sponge. Because without that sponge, we've got cactus. Nothing. Dead. Desert. Now we can forget all about that and we go into the important stuff. Because once we have a sponge with water in it, obviously, what we have in a sense the capacity to grow biosystems. We already talked about that, longevity of green. And we've got transpiration, right? Water going up is transpiration. And you and I and everybody knows for every gram of water that transpires, it has to go from liquid to a gas. And to go from liquid to a gas, every gram needs to have 590 calories of energy in its latent heat of vaporization. Simple physics. And so 590 calories of energy have to be taken from this soil surface, from where the water is, and from the vegetation. And so we can't avoid but cool this surface. That heat, of course, goes up when this water condenses. It again gets released, and most of it goes back out to space. Okay? Nature has really driven the hydrological cooling of the planet by these latent heat fluxes. Even now, with half of the green vegetation on this planet, the residual green vegetation we talked about, 24% of the incident solar radiation, that 342 watts coming in, some 85 watts per square meter, is constantly taken back up through these latent heat fluxes. Okay, so that green vegetation is constantly taking 24% of the incoming energy that's striking the surface and taking it back out to space. So if we 5% increase in green transpiration, we can effectively negate 3 watts per square meter, roughly, right? It's obviously many factors of things. So the fact is, the 3 watts per square meter, how do we cool the planet 3 watts per square meter? Simple. Increase transpiration 5%. And we're running at half of what there was 8,000 years ago. We're running at 50% of what there was. Okay?
I was just thinking, think about all the bare ground that's out there. It's not doing any transpiration.
Yep.
Bare ground is what's killing you.
We'll come to that. Okay, come to that. Okay, so here we have, in a sense...
Just a brief comment. There was, in the upper Midwest, they stopped leaving land fallow, and a study of that showed that just that one thing, covering that land all year round with green things, brought down the watts per square meter by a factor of 6 watts per square meter. That's double.
Yep. I live in a city called Canberra, which is Australia's natural capital. It was designed and built from 1913 onwards. Marion Mahoney, Walter Burley Griffin won the prize. They made a landscape city. It was a leading city for the 20th century, what urban future habitats need to look like. And of course what they did, Canberra initially was what we called a clapped out, arid, dusty, dried out sheep paddock. And basically they built an urban forest and really created a whole new mesic, forested, urban forest environment. It's now 7 degrees centigrade cooler on a hot summer's day, 35, 40 degrees centigrade, than the adjacent urban heat island concrete new suburbs, 2 kilometres away, right? 7 degrees centigrade cooler. So absolutely, and it's all just because of latent heat fluxes. So again, we in Canberra, we've got a thing, from the grassroots called Cool Canberra, and it's all about urban trees, about porous pavements, about sponge infiltration to keep these latent heat fluxes But it gets better, so let's keep going. Obviously, we've got these hazes and these latent heat fluxes condensing into cloud, little droplets, and of course releasing the heat. So we end up with massive numbers of cloud micro droplets, right? Okay, but these are far too small to fall out as rain, and of course they sit up there as hazes and as clouds. But then they'll basically form these nice white fluffy things, right? Somebody asked about clouds before, right? So they'll form dense, high albedo clouds. There's a coalescence process involved, but we can go through the physics, but I don't want to waste time on it. But the point, these dense, high albedo clouds, they basically reflect, because it's an albedo effect, they reflect that incident solar radiation directly back out to space. It doesn't even get to the soil surface. You know, when a cloud comes over, hey, you're reaching for another jumper. It's significantly cooler. These guys, globally, 50% of the Earth's surface is covered in dense clouds at any one time. Or certainly used to be, it's getting less. But 50% of the surface of the planet is still covered in clouds at any time. These guys on average reflect 120 watts per square meter back to space. Okay? About a third, roughly, of the incident solar radiation is just reflected back out to space. So again, the same analogy, a 2% increase in cloud will offset 3 watts per square meter. Okay, and cloud can only happen if we get micro droplets, and they can only happen if we have a sponge that's transpiring water up into the air. Okay, so you can see all the time we bring it back to the sponge, because the sponge is a fundamental driver, but also the sponge is what we influence. That's our point of agency. A, B, C, D, it's what we can do. Every square meter, every acre, every region, every nation. Grassroots empowerment of action. Okay, so there's clouds. But we talked about the sponge being critical, but that's not good enough having clouds, because we also need this next guy. We need raindrops, don't we? Because if we have a dry sponge, cactus, no good. So we need rain. And it takes about 1 million of these cloud condensation droplets to form a raindrop, because it's got to coalesce about 1 million of these cloud micro droplets to make a raindrop that's big enough, heavy enough to fall out under gravity. There's 3 things that actually allow you to do that. They're called precipitation nuclei. Okay, rain can't occur just by itself. They have to be precipitated through these precipitation nuclei. 3 things. There's ice crystals, and of course they're very important high altitudes, high latitudes, and frontal rain. It gets colder, it forms ice. You know, a glass of whiskey, ice will coalesce on the outside, condense on the outside, same process. So there's ice crystals. Over the ocean, of course, we have a lot of salt. Spray comes up from the oceans, and again, salt, sea salt, we know on the fish, in the ocean, shake the salt shaker, it's all gluggy because it's hygroscopic. It sucks up water, won't come out, and again, it's basically coalescing these droplets. And of course, it's these salts that we use for cloud seeding, where we use, for example, silver iodide to create artificial rain. Basically, we go up with aeroplanes, atomize silver iodide, drop it into particular types of clouds, and consistently get 20-30% more rainfall through that process. Okay, but by far the most important thing, particularly on inland areas and tropical and warmer areas, are not these, but this bacteria. There's certain bacteria, and Louis Pasteur wrote about them, defined them, isolated them in the 1870s. He called them Aerobacter orogenes because he certainly found them in all the air, but he didn't know what they were doing there. So in Greek that translated to, yeah, I don't know what they're doing there, orogenes, right? Well, he was a scientist. He's got to be objective about it.
So long as it wasn't erogenous.
Sorry?
Just so long as it wasn't erogenous.
Erogenous, yeah. Well, that's Parisian, isn't it? But the point is, there's bacteria, right? And so these in cloud, CSIRO, atmospheric physics, again, detailed work we did, by far the most effective at nucleating clouds into raindrops, by far, orders of magnitude. But of course, atomizing bacteria to disperse in the atmosphere is a bit sophisticated, and until recently we weren't able to do that. But these actually are produced in nature, and of course what nature does, in certain forests, and again we've got this from the Amazon, a whole lot of studies, basically it's not just transpiring water vapor, it's also putting up bacteria. Okay, and so half the rain, this is from radioisotope studies, half the rain in the atmosphere, the Amazon, is actually driven by these bacteria. It goes up, transpires every day, 4:30 in the afternoon, you set your watch on it, it comes back down in a thunderstorm. And every day you've got this hydrological cycle taking heat from the surface, dissipating it upstairs, returning rain back to the sponge. Okay, and vast areas of forests have been cleared. We've talked about the 8 billion hectares of primary forests that we've cleared, 6.3 billion hectares of. So what have we done to our rain? We can write a song about it. Okay? And so this is a question again, by regenerating landscapes, can we actually start restoring these hydrological dynamics? Because these are critical if we're going to refill this sponge. Okay? So it all comes back to, cooling, rain, more cooling. Okay? Powerfully natural, simple, safe processes to cool regions and the planet. We need rain, we can cool the planet, but it all depends on the sponge. And of course somebody made the point previously, there's a vast difference where we have two land systems. Here we've got a land system with plants, grass, green, and here we have a bare land surface, right? Vast differences, because this one is both getting latent heat fluxes, so it's cooling, and very rarely does this soil here get above 20 degrees centigrade. Okay, because it's got latent heat fluxes cooling, but it's also got the albedo and shading and cover effect. But we know that a bare surface, whether it's soil, asphalt, roads or whatever, readily gets up to 60 degrees centigrade, right? Certainly in Australia. You melt your feet. Way past your feet, your shoes as well. Okay, and what it is, it's of course this incident energy coming in, heating these systems, and of course how much is actually taken back up. Vast differences in things. But there's again a simple fundamental law of physics, the Stefan-Boltzmann equation, because the Earth is a black body radiator. It's like a stove. And the black body radiator, the Stefan-Boltzmann says the re-radiation from a black body is proportional to a constant times the fourth power of the temperature in degrees Kelvin. That means temperature times temperature times temperature times temperature. So when we have two different surfaces, one at 20 degrees centigrade and one at 60 degrees centigrade, we get a massive increase in the re-radiation of heat, infrared energy, from this bare, hot surface. Okay? Massive increase. Now, the punchline is, we all know that, but what we don't recognize is three things that control both the natural and the artificial greenhouse effect. The first factor is how much re-radiation there is. The second factor is how much of that is absorbed by water vapor molecules. And the third factor is how much is absorbed by CO2 molecules. 3 variables in both the natural and the artificial greenhouse effect. And the point is, we have completely ignored in all our climate models the effect of land management and these bare soils and this re-radiation in driving the greenhouse effect. Completely ignored it because we said, oh, well, look, you know, that's just the planet and we're concerned about CO2. There's up to 40,000 parts per million water vapor in the air in these humid hazes. We know there's 400 parts per million of CO2, 406, let's be straight, parts per million of CO2 in the air. We know that each water vapor molecule, because of its molecular structure, holds 8 times, or can absorb 8 times more water than a CO2 molecule, 590 calories compared to about 72 calories. And yet, we're only concerned about this variable, and we can't do anything about that variable for 1,000 years. And we're saying, hey, doomsday, game over, can't go forward. And we're more or less saying there's a new solution to climate change because basically we control this guy, and this runs 90% plus of the greenhouse effect. We control this guy, we've just gone through that in terms of rainfall, you know, induction, etc., etc. And yet we're all focused on that. But we need this because this is the building blocks for building bed springs. So we're into building bed springs through drawing down carbon to build the sponge. But what we're saying is, let's just get real. You know, we've got a climate extremes, climate crisis. We've got 10 years, so let's start talking to the elephants. Because we can do this, and whether we do this instead of that is existential. Okay, so really we've got, again, we're just talking about empowerment. So through our land management, we have an enormous capacity to both cool the planet but avoid these dangerous extremes that we're facing. There's another thing. When we actually re-radiate a lot of heat from these bare, dry, hard surfaces, obviously this heat is just energy, and so this creates a very high-pressure dome, heat dome, right? Okay? And we talked about, I mean, this is the question I think you raised. So we create this massive high-pressure heat dome because of this re-radiated energy. And so if we look at a country, and let's look at your country, because we've got the ocean, we've got the coast strip, we've got the coast range, we've got the Central Valley, we've got the Sierra Nevada, we've got Death Valley, and then we go on to the Western Plains. Okay, and the point is, if we, for example, take the Central Valley, and we clear that Central Valley in California, the San Joaquin Valley of vegetation, what we do is we create a high-pressure heat dome over that landscape, right? And of course we've got cooler, moist, low-pressure air from the oceans flowing in, but it's got Buckley's, which is an Australian word for no chance whatsoever, to be able to push this high-pressure heat dome out of the way.
What?
Yeah.
Sorry, maybe say all that again.
Oh, okay. So what it is, if we have cleared this landscape, we're in this position here, we've created a high-pressure heat dome because of all the re-radiation coming off thing. We have, in a sense, this mountain of hot air sitting on that landscape. We have now low-pressure air, which has got moisture in it from the oceans. There is no way in physics that this flowing into that area can actually, this moist air can flow into that area. Okay? And so really, we are actually desertifying regions and climates through our land management. The bottom line is, as we've gone through this whole extended discussion, yes, there are new paradigms. There are new doorways, new opportunities that we can use to naturally cool the planet, to address climate change, but also to secure the water, the food, the biosystems, the social stability that we just agreed depend on that. As the gentleman said, there's 7 missed meals between social stability and chaos. And that all depends on water, food, social stability, a la Syria. And the answer to this is critical, important. Yes, Mark Twain said, whiskey is for drinking, water is for fighting over. Okay, and it's true. And that's where it's going to happen. But the point is that these natural processes give us the option, an opportunity to secure endless, safe water. There's plenty of water on this planet, but it just has to be, we just have to come to respect it and rebuild the cycles. But the point of agency and the point of this whole discussion is it's about regenerating the Earth's soil carbon sponge. Because by drawing down that carbon to put the bed springs into between those soil particles, we can do it profitably, practically. We can actually rebuild the sponge, and as we've seen, ABC, etc., we can actually then restore healthy biosystems and a healthy future for California, but for all of us. Thank you very much.